Generalized derivatives. If g of t is generalized function, its nth generalized derivatives g power n of t equal to d power n g of t divided by d t power n is defined by the following relation. Del over minus infinity plus infinity phi of t g power n of t dt equal to minus 1 power n del over minus infinity plus infinity pi of n sorry pi power n of t g of t dt, where pi of t is a testing function. Pi of t is a testing function which can be differentiated an arbitrary number of times and vanishes outside some fixed interval, and pi power n of t is the nth derivative of pi of t thus by equation 2, and that is 1.28 and 1.20. Derivative of del of t can be defined as del over minus infinity plus infinity pi of t till 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 dash of t dt equal to minus pi dash of 0. That is, yeah, we already have seen this one, this equation. Pi of t here nth derivative, that's why coming here n, and the g of n is generalized, that's why here g of t, g power n of t coming here, g of t dt same coming. Pi of t is the testing function, can be differentiated an arbitrary number of times and vanishes outside some fixed interval. Pi of pi power n of t is the nth derivative of pi of t, thus by equation 1.28 and 1.20. Okay, the derivative of del of t can be defined as minus integral over minus infinity plus infinity pi of t del dash of t equal to dt equal to minus pi dash of 0. Pi t is the testing function which is continuous t equal to 0 and vanishes outside some fixed interval, and pi dash of 0 equal to d dash of t divided by dt, condition t equal to 0. Using 1.28 equation, this equation, the derivative of u of t can be shown to be del of t. Probability problem 1.28, that is del of t equal to u dash of t equal to du of t divided by t dt. Phi of t is the testing function. Testing function for which is function going to testing, that one is called phi of t. That is testing function which is continuous at t equal to 0 also, it is continuous and vanishes outside some fixed interval. Then will be delete outside some fixed interval, and phi dash of 0 equal to t pi of t divided by dt t equal to 0. The derivative of ut can be shown del of t, the derivative of u of t derivative del of t equal to u dash of t means derivative equal to du of t divided by dt. It means u differentiate with respect to dt. This is equation 1.30. Then the unit step function e of t can be expressed as unit step function. Already we have seen last video in the figure. E of t can be expressed as e of t equal to integral over minus infinity to plus infinity del of tau d tau. This is equation 131. Note that the unit step function e of t is discontinuous at the t equal to 0. Therefore, the derivative of shown figure, the derivative of e of t as shown in equation 1.30 is not the derivative of a function in the ordinary sense, and it should be considered a generalized derivative. In the sense of a generalized function from equation 1.31, we see that e of t is undefined at t equal to 0 and e of t equal to 1 condition t is greater than 0, 0 when t is less than 0 by equation 1.1 with phi of t equal to 1. This result consistent with the definition 1.18 of e of t, that is unit step function e of t can be expressed e of t minus infinity to not plus infinity t particular distance only. Okay, t minus infinity. Okay, minus infinity. Del of tau differentiate tau. Note that the unit step function e of t is discontinuous. Note that the unit step function e of t is discontinuous at t equal to 0, where when the discontinuous is e of t equal to 0. Therefore, the derivative of e of t as shown in figure, shown in equation. Therefore, the derivative of e of t as shown in equation that is not the derivative function in the ordinary sense. It's not a derivative function in ordinary sense, and it should be considered a general derivative. General derivative in the sense that of a generalized function. From equation 1.319, we see that e of t is undefined. We see that e of t is undefined at t equal to 0. So e of t equal to 1 when t is greater than 0. When t is less than 0, that time e of t equal to in this unit function is 0. Unity function, unity step function, not unity function, unity step function e of t. By equation 1.1 with phi of t equal to 1, this result consistent with the definition 1.18 of e of t. Equation 1.1 with pi of t equal to 1, this result consistent with the definition of 1.18 of e of t. Complex exponential signals. Complex exponential signals. The complex exponential signal x of t equal to e power j omega naught t. Complex exponential signals. The complex exponential signal e power j omega is the complex exponential signal. That is x of t equal to e power j omega naught t. Here exponentially increasing sinusoidal signal, exponentially decreasing sinusoidal signal. A exponentially increasing sinusoidal signal A. This is exponentially decreasing sinusoidal signal A. It's an important example of a complex signal using Euler's formula. This signal can be defined as using Euler's formula. The signal can be defined as x of t equal to e power j omega t equal to cos omega t plus j sin omega t, omega naught of t. Euler's formula, the signal can be defined as x of t equal to e power j omega naught t equal to cos omega naught t equal plus j sin omega t. Thus, x of t is a complex signal whose real part is cos omega t and the imaginary part is sin omega naught t. An important property of the complex exponential signal x of t equation 1.32 is that it is periodic. The fundamental period t naught of x of t is given by 1.9. T naught equal to 2 pi divided by omega naught. Note that x of t is periodic for any value of omega naught. Note that x of t is a periodic for any value of omega naught. General complex exponential signals. General complex exponential signals. Let s equal to sigma plus j omega be a complex number. We defined x of t as x of t equal to e power st equal to e power sigma plus j omega of t equal to t sigma t cos omega t plus j sin omega t. General complex exponential signals. Let s equal to sigma j omega be a complex number. We defined x of t as x of t e power est e power all sigma plus j omega of t equal to e sigma of t into cos omega t plus j sin omega t. Then signal x of t in equation 1.3 is known as general complex exponential signal whose real part is e power sigma t cos omega t and the imaginary part is e alpha sigma e power sigma t sin omega t. For exponentially increasing, sigma is greater than 0 or decreasing, sigma is less than 0, sinusoidal signals. Real exponential signals. Note that if s equal to sigma, a real number, then the equation 1.